So, welcome everybody. So I'm Martin, one of the tutors for the 2015 Shanghai lectures. I'll go through today the koans for the group projects, and please feel free to stop me at any time if you have questions, otherwise we can take questions at the end. So the koans are basically challenges for the student group projects. As you know, the student assessments that we have this year in Shanghai lectures is based on group projects, and a koan is defined, according to Wikipedia, as a story, dialogue, question, or statement which is used in Zen practice to provoke the great doubt and test the student's progress in Zen practice. So it's a half series, but it's meant as a challenge in the sense that these project topics that we give you, these koans, are not meant as something that necessarily have one correct answer. It's meant as something that should cause you to sit down and try to apply what you learn in class to a challenging topic. And you shouldn't expect that any of us either have the correct answer to it. So don't feel scared, just go at it as best as you can. The koans are now published on the koans page on the website. So you just go on the lectures, koans. And here is the timeline. So they're basically published today. Then you have until the 5th of November to select a koan. And then on around about the 8th of November, we'll publish the student groups. So we'll try to distribute you into different groups. You will have two things you have to hand in, or one thing you have to hand in basically is the preliminary design report on the 3rd of December. I'll talk more about that later. And then you have the group presentations end of January. So the grading then is 25% the preliminary design report. For all students that participate in the Shanghai lectures, you will get a certificate of participation. If you do complete successfully the koans and the group projects, you will also get a certificate, koan certificate with the grade and everything. So the preliminary design report is 25%. We prefer this to be a wiki on whatever repository you choose to use. So we like this year for every group to publish everything they do, documents, code, printable files, models, etc., on a repository like Bitbucket, Gitcafe, GitHub, and then the wiki could be your preliminary design report, or you could hand in a 4-page written report. So these are ideas, plans, and the current progress, and this will be graded by your tutors. So you'll typically have 1 to 2 tutors for each group. And the tutors are typically PhD or postdocs working in related fields. The group presentations is 75%. This will be end of January, and we typically do that by Google Hangouts. So we connect up everybody in the group with a small presentation panel made up from these tutors and also some of the other people working in the Shanghai lectures. And then you basically present your project, kind of like we do now, but over Google Hangouts. I'll give you more details on the specifics of this as we get closer to the deadlines. Here's some examples of what koans has been shown in the past, or been done in the past. You can see there's a wide variety of things that students have looked at. Evolution of robots, investigation of gait, of symbol grounding, optimization of manta ray wings, passive manta ray wings, the soft bodies. You can see a lot of screenshots from Webbots here, so that's one of the main simulator that we use. And we also try to, at least this year, we will try to encourage the usage of hardware. So try to get the students to actually build something from the group projects. And you can find all these previous presentations on our Koan's YouTube channel, and we also have a Google Plus page, so do check it out, and you can get inspiration from what people have done in the past. All right, so I'll start with the koans now. There'll be 12 koans in total, and you basically have to choose one of these. The first one is called soft catch. So this is about reliably, basically, it's hard for a robot to catch objects, but there are certainly progress being made, as you can see in the top right-hand corner here. You can see a robot catching almost any object that's thrown to it. One thing you might want to notice is that, just as we said last week, there are no labels in the real world, neither are there typically markers in the real world. And these objects will all have some kind of markers that are tracked globally at a very very exact system. So the idea of this koan is, okay, can you try to do something similar but with a soft robot arm? Something like what you see in the bottom there. So how can a soft robot arm help you catch something? For example, if you're catching something a little bit heavy and the arm starts actually deflecting as the object hits the hand, how does that give you extra time to actually close the hand, for example? And does this simplify the control? So we put in a couple examples here that can inspire you. Yeah. That's that koan. Koan 2 is called From Passive to Activated Dynamic Walking. We saw in previous weeks the passive dynamic walkers and how they exploit their own intrinsic dynamics to generate a natural and energy-efficient gait. However, typically you would have to put them on a slope, although there are nice little implementations like this Cornell Ranger that was able to walk 65 kilometers on one charge. Can you try to make a passive dynamic walker that can do something, actually approach a nice normal gait that can do something interesting in the real world? For example, how can you change the speed? Could you add sensors to the feet? Could you do reflexes? And do feel free to think about hardware implementations if possible. For example, through 3D printing, you can do quite a lot of interesting stuff now. Koan 3, take puppy out for a walk. So this little robot here, I think you will see later in the lecture series, basically very simple quadruped robot with one servo in each hip, and then you have this passive compliance through a spring in each knee joint that allows it to actually obtain quite interesting gaits. You can just Google it or check out this demo puppy, which is a 3D printable version of it, and there's videos of that running around. So how well does this work, for example, in an uneven terrain? Can you try to explore this either in a simulator? We've had students done this in WebOS before, but you can also try to make this real implementation by 3D printing it. Could you improve performance? Could you perhaps add sensors, reflexes, etc.? Okay, koan 4. So this is about learning how to swim like a fish. So once in a while we discover fossil remains of fish, which gives us insights into the evolution of the species. However, the way they lived and the way they moved is quite hard to kind of ascertain that just from looking at these fossilized fishes. So the idea of this koan is to try to design a robot fish and a machine learning algorithm to try to make this fish swim around in an interesting way, in a useful way. And can you gain insights on the way extinct fishes actually swam? That'll be very interesting to explore. And again, there are ways to do this in 2D simulators, 3D simulators, but again, we could also try to do something in hardware, possibly. There are hardware solutions for this. Koan 5, a soft touch. So this is about exploring hands and arms with different degrees of passive compliance. This could be as simple as rigid links connected by springs. And then implement a physical design, for example, 3D print, or you do it in a simulator. An example is the iHigh hand from iRobot, Harvard University and Yale University. Do check out the videos, and also check out the Soft Robotics Toolkit. There's a lot of cool stuff up there on soft robot designs. And then you could do things like, for example, how can you grasp an object by simply letting your hand fall on top of it and then closing the hand? How many actors should you use? How many fingers should you use? Again, there's no one correct answer to this. This is for you to explore and come up with something interesting and publish on your repository so people can actually reuse it. And then discuss the impact on controller design and movement planning required. Again, can you simplify these things by having a softer approach to grasping? Quant 6, evolution of brain and body. This is something you'll learn more about later in the series as well. But basically in humans and animals, the brain and the body and the environment to a certain degree have been evolved together over millions of years. So this is about exploring this type of co-evolution of brain and body. And perhaps also the environment, and can you come up with some interesting new morphologies, new behaviors that actually take advantage of these two things, or the body and the brain being evolved together. You could use webbots. There's a Yamor modular robots. You could use Bongard's Ludobots or any other suitable simulation suite. And then what benefits can you find for evolving the mind and body concurrently, and how can it play a role in future robot designs? Quant 7, wearable soft robotics. We know soft robotics provide a tool for making safe and comfortable wearing wearable devices. You all remember Back to the Future, I hope. So design a wearable soft device and fabricate a prototype of it, and please use your imagination. Again, good place to start is the Soft Robotics Toolkit, BlueFlex tutorial, jam sheets, the result. All the links are on the page here. And then how is the soft mechanism coupled with the human body, and how is this related to the lecture topics? That's that Quant. Quant 8, we've seen a little bit of this already. But this one is about useful robot collaboration from local rules. So you are to implement a swarm of simple robots of your choice in any large virtual environment. It could be a school of fish, it could be a flock of birds, it could be something else. And then have a look at these simple behavior rules. For example, that the robots move in the same direction as the neighbors, remain close to the neighbors, avoid collision with the neighbors. And then look at what events can trigger a reaction and how this reaction could be somehow useful to the flock. For example, response to predator attack or response to food. So that's that Quant 9, iBot Sim. I don't think they covered this yet, but I think this will be covered later. This is basically replicating an experiment by Lichtensteiger and Eggenberger, either in simulation on a real robot, that basically tries to emulate the way houseflies have a higher density of eye facets towards the front, which compensates for motion parallax, and it's just a cheap design. So it makes things kind of makes it easier to make behaviors based on this vision because of the morphology of the vision sensor. Can you replicate the experiment on a robot, for example, in webbots on a real platform? Can you find other examples of morphological computation in nature, perhaps other insects with a similar or other interesting sense of morphology? And what is the potential for evolving this type of sense of morphology for robots acting in the real world? Quant 10 is an interesting one, passive walking and hopping on a comet. So last year we had the first landing on a comet. The little lander in the low gravity field there at a very low equivalent weight. So moving it was very hard. So can you have a look at things like passive walkers, passive hopping devices like the one you see in the picture here, and perhaps design something simple for the European Space Agency or whatever space agency wants to go to another comet to move around on that comet in a nice, simple way. And Quant 11, again, space theme, evolving robot explorers. So we know there are 9 oceans outside Earth in the solar system. The oceans of Europa and Enceladus are the best candidates so far for search for extraterrestrial life. They pretty much have everything needed, and they can be really large, deep oceans. So how do you plan robot exploration of these distant worlds? A solution might be provided by sending a self-evolving species of evolving intelligent robots. And then think of a basic set of co-evolving morphology and intelligent robots. This is quite an open one. And then Koan 12 is basically define your own Koan. Okay? So do you have an idea that you'd like to explore? Is there something related to your current research, to your research group? Is there a group of students interested in the same thing? Well, just send us an email and we'll try to help you organize it. There are 2 conditions you have to satisfy. That has to be related to some of the topics covered in class, which should be quite easy. And the other is that the group must also be open to other students, although we have a maximum of 5 students for each group. So that's the koans. They're all on the koan page on the website now, so you can look at them at your own in your own time. As for the student groups, they will be assigned according to koan preferences. So as I said, max 5 students per group, and we do aim to make the groups as international as possible. Again, we do encourage Harvard solutions. Although we have great simulation software as well, such as webbots, etc., that are available to you. But if you have a local piece of hardware on your site, then it is okay that you can suggest to have a local core of students working on that, as long as the group still remains open to students from other sites. And I should stress this again, thinking outside the box is required. There are no single correct answers to any of these koans, so please feel free to be creative. This is basically, if you want to participate in the koans, this is what you have to do now. You should go to the website and create yourself an account there as a student, if you haven't already. Then you can sign up for a koan following this link. It's also on the web page, on the koan page, so don't worry, you can just go to the koan page and go from there. It's a document in Google. If you can't open the document in Google, just send me an email with your koan preference. That's also fine. And then start playing around with webbots. Highly recommended. Install a 30-day trial version. I can get that from Robotics. And if you do, when you do install webbots, please use the same email registered on the Shanghai Lectures website account, so that we could potentially extend your license in the future. And that's pretty much all from me. If there are any questions, it's a good time for the students to ask questions. Anybody? Okay. So Nathan, is Fabio connected?
So welcome. Welcome everybody. There is some echo.
Could all sides please make sure that the microphones are muted? Thank you.
Okay, so I will continue the main track, and the idea is to make you, the students, participate a bit as much as you like. So the main topic of these lectures is, as Rolf pointed out, and how it is spotted by the few guest lectures that we already had, and the many more that you can find on our website, is natural intelligence. No? Well, how natural and artificial intelligence. So we have this double interest. On the one side, it's a pure scientific interest. We want to understand how things work in nature. How is it possible that there are, if not, because it might be a bit early, whatever people fear, to understand human consciousness, just understanding how an ant or a rat works, it would be already an enormous scientific success. On the other hand, we hope to use this kind of understanding to build machines, right? And this is not new. So this, what I'm showing now, which is a Swiss example of robots, of mechanical robots of the end of the 18th century, it's not the very first. The very first examples, even of automatons, are in the early Chinese civilization. We already have some example, 2,050 years before Christ, so almost 5,000. So this idea of building some mechanism to do useful work is not new at all. What have in common these automatons with the Swiss automatons, with the previous example, and the Karakuri dolls? Now, the Karakuri dolls are similar exercises, similar machines, more or less built in the same period in Japan. So essentially, they have a machine, so an arm. You see, it's very, I think it's very understandable. You carve in wood an arm, you connect it with some kind of wheel and gear, and then you organize wheel and gears like in a clock to obtain the behavior that you want. And this is possible, right? In modern view, what the difference with a modern robot is that in both cases we have a mechanical structure, the structure of a doll, in this case of a Karakuri doll, and we have an automaton that, in the case of the Karakuri dolls or the Jacquet Draw brother in Switzerland, are essentially clocks. So you have a finite state automaton, a machine, that is, in the case of these old examples, is implemented with a clock, so with a mechanical structure similar, which is, but essentially is a state machine. So something which moves from a state. When it is in a state, it will activate certain levers or certain pulls or certain gears. While in the modern case, you will have a microprocessor or an array of microprocessors. Where is the difference? So you see any difference? What's the main difference from this perspective from a Karakuri doll and Asimov? Any idea? Because there is a difference, no? Conceptually, I can claim that they are the same thing because they are state machines. But in the case of Asimov, with respect to this T7 doll from a couple of centuries ago, where is the main difference? Domanda anche per le persone. No, the main...
Così me la spieghi bene.
No. No, okay. The main difference, of course, is the number of states and the complex. So what the digital implementation gives us that they hadn't is the possibility to manage much more states and much more procedures. So the factor of having, because Rolf was talking about the functionalism, no? The functional attitude, that it doesn't matter if it is a microprocessor or a Swiss cheese, I can implement the same logic. And actually, nobody did it, but I may connect a Karakuri doll or a Swiss automaton to, instead of to a clock, I could connect it to a program on a microprocessor, which may or naively simulate the clock. Now, I may implement, this might be an idea, I may implement in Webots a Karakuri doll. Right? It might take some time, But it would take less time if I write the logic instead of by means of gears. I write the logic into a Python program. So this is the main advantage. Now, a lot of automation that we already see around us actually use this simple fact that from thanks to the Moore law, the number of logic behaviors that we can stack into a machine is growing all the time. No? And so if you hear a bit kind of provocation, so but again there was also, but this is not the older example. No? In the times of the Spanish Empire, actually an Italian living in Spain, Juan Toriano, was able to build simpler but I would say karakuri dolls for the powerful person of the times, which was the Emperor Charles V. And today, this is not the latest example. Thanks to silicon, now you can. If you think to this Android, basically, you have a surface Androids. You have a surface of silicon, and you have a number of small mechanisms behind the silicon, that you can program to simulate an expression. So it's a complete area of research, because actually how we understand that an expression is an happy expression or a sad expression, and all the many nuances that are able to detect. No? So when the game is, you understand by studying humans which are the face expressions that we recognize, doing tests with different people, because not all of us are empathic, sympathetic with other people's emotions to the same degree. So it's possible that someone needs a very angry face to understand that someone is angry, and another person just understands from a slight change in your smile that you are not a bit upset, right? And the same for the robot. So how to think to the exercise that they do with these androids, what you essentially do is building a lot of leverages and try until you get the expression that you want. And I'm not going to show you a video now, but if you think to what you may, if you look, for instance, for Ishiguro Hiroshi androids in YouTube, you will find really a lot of very impressive examples of what I mean. What I pretend, what we suspect is that conceptually there is not a difference with Juan Toriano. No? Juan Toriano wanted to show a monk praying, and he had implemented some very simple mechanism. He wanted a girl playing the lute, and he just programmed something like this. With much more computation power, so with a much more potential complexity in the state machine, Hiroshi Shiguro and many others are able to, for instance, Minoru Asada, who was a guest lecturer here last year from Osaka, has a very nice Leonardo da Vinci android in the Expo, in International Expo in Milan. So conceptually, we do something which is very similar. What is different is that the program is much longer, much longer, and much more complicated, with much more blocks. I think that you are all grown up enough to have seen many block diagram of programs. Of course, to implement something like this Ishiguro androids or Zada, and there are many others. Well, not so many so good, but there are many others. And it's a lot of work. You need a lot of people working. So if you are a company, a lot of people working in the company. If you are a university, a lot of people working in the project on that project. Now you need many people. So let's see what I want to talk about today. Essentially, I want to figure, and I already started to do that, to put the issue of the study of natural intelligence in context. Now, what we are talking about, not only from a theoretical standpoint, but I think we already have seen this under many respects, but also from the economical standpoint. No? Because I may dismiss this approach, this standard approach, the top-down control, the good old-fashioned AI approach, but it's true that already now, with the technologies that we have available, we expect a tremendous spreading, a significant spreading of robotics technologies all around the world. So these are some, I think, conservative forecast of the robotics market in Europe in the next, say, 10 years, right? Made by Robotics, which is the the main association of people active in robotics, both research and industry in Europe. So what we expect is a growth of 8-9% per annum in this area, which and we expect that right now, already now in Europe, worldwide, we have $20 billion of a market which is has a turnover of $20 billion of dollars, which is not a small amount of money so it's not anymore niche activity. So it's not anymore researchers playing with robots. No, it's becoming an important area of economy. And we expect that in 5 years it will be, we don't know exactly if 2 or 3 times as much. So it's really a big story. And then we are starting now, because talking about Go-Fi, right, good old-fashioned AI. So already we are seeing a huge penetration of this simple model. So the fact that the stupid model implemented by Juanelo Toriano or in the South Sun Chariot in China almost 5,000 years ago, adding the computing power made available by Moore laws is already changing the world. So, so we are actually seeing a number of technologies starting from new components, like the MEMS that you are in your cell phone, the Internet of Things. So the fact that we don't need the robot to be able to really understand where it is if I put some beacon and if I instrument this room or even the streets of my life. So this should already, and it's, as I told you, it's probably a conservative estimate, create a huge amount of revenues in a new market. So this is also important. And many people are already worrying about what may happen to most of the jobs. There is, I will leave this for a further lecture, but if you do an analysis of what can be automated by this stupid old-fashioned approach, it's already a lot. So there is a study, we will see it in more detail, by Oxford people, from a group of people from Oxford University, showing that in 10 to 15 years, about 40 to 47% of the actual tasks in the economy today, from clerk work, white-collar work to blue-collar work, is going to be automated. No? So what does it mean? This is an issue that we are facing right now, because the two extremes are 80% in 10, 20 years, 80% of unemployment and collapse of economy, or you may have a kind of Greek-style society where the humans are the citizens of a Greek city, and the slaves are the robots make the slave labor, right? So these are two extremes, but we have this kind of challenge over. Then I was talking about, this is of course this is our, I mean, it's not just my view, it's our institute view. It's a kind of an attempt to understand when GoFi and the mechatronic approach will run out of steam. No? So this is a kind of periodization of what we expect to happen in the technology used by people building stuff. No? Because I mean, personally, I am a curiosity-driven person. So I am in academia. So I'm really curious to understand how natural intelligence works. But I'm also a citizen, and I'm interested to see what I can do for the community. Right? So what we expect is going to happen. So we may say that we had from 1990 to the year 2000, we had a bunch of applications based essentially on this mechanism. So state automaton implemented in a microprocessor or an array of microprocessor using control engineering, typically the good old-fashioned linear control, PID, for those of you who already attended the control course, and with good old-fashioned computer science. So algorithms, and algorithms. So algorithms on a microprocessor driving a rigid mechanical structure by means of linear controls can explain most of the things that we see today, or even plans. So the Roomba is a thing like that. But about this, what we are seeing today, so around the year 2015, is that we start to use some real AI, and we mean essentially the good old-fashioned AI, symbolic AI, so massive implementation of AI programs. We are starting to see machine learning, so algorithms that statistically, so the main strength of machine learning and the fashion or deep learning is that it hasn't a predefined model of the world. So they build the model by statistical inference using base rule, basically. No? And the Internet of Things. So if I don't know how very well where I am, I put a couple of radio emitters in the right places, and then I triangulate and I know where I am. So I can instrument the space. In this way, I can do many things. So the things that you have seen in the previous slides about what you can do in terms of dollars, but it's essentially when you devise a new product, you solve a daily life problem, is enormous already. So when this kind, what we are talking now, we think will start to be important also from real-world application. Well, we think it will start to be used in the next 10 to 20 years, depending on the funding for research and depending on how smart we are in fixing the issues that are in front of us. So, what we expect is that we are essentially surfing the wave of machine learning, AI, and Internet of Things, which is actually based on good old-fashioned mechanical engineering, good old-fashioned computer science, good old-fashioned control engineering. And while we surf this, we already have in front of us this kind of theoretical challenge, which are morphological computation, a thing that we talk about, which is a simplexity, and the emergence and self-organization, which are different forms of bio-inspiration. So nature is working in a different way than our current technology tools. And now maybe Nathan may show first the Asimov video and then the other one, the inner life.
私、足のことをたくさん知ってもらいたいと思います。私たち人間にとって自然というのか、歩くということ。2本の足を交互に出して歩く。段差や階段を上る、降りる。凸凹な道や坂道を歩く。歩くといっても、実は人間はさまざまなバランスを足でとって歩いているのです。だからロボットにとってはとても難しいことなのです。その2本の足で歩くということを世界で初めて実現したロボット、それがアスムなのです。今私は足の裏のセンサーで階段を確認し、うまくバランスを取ること。皆さんついてないでしょうけど、人間も
No, okay, I think that many of you have seen this many times already. So the point here is not that Asimov as being badly designed or that it is not a good system. It is, I would say, close to perfect. So what happened? Now we can see the other video. So this video that you see is actually a simulation, a 3D simulation based on real scientific data developed a few years ago by the University of Harvard. And what it's apparent at first glance is that the principle of design, it's not a design, no, but the organizational principle of a cell are completely different from the methods that we usually still, and for sure the industry in most cases uses to develop robots. So while in the first case you have top-down control, you have someone knowing in advance what the robot is going to do, and recently you had some statistical inference on a huge amount of data. That's how self-driving cars are able to drive. On the other hand, you have a completely different paradigm. You have many components loosely connected, where the useful behaviors emerge from the collective interaction and the interaction with the environment. Where is the problem? The problem here, why we don't do that? Well, you have a couple of serious reasons that prevent you from doing that. One is material, so we are not still able to engineer tissues like those that we see in the biological world, animals but also plants. The other issue is that really we have an idea, and I would say that what it was written by Rolf already many years ago is in the couple of books that we have quoted now, Understanding Intelligence and How the Body Shapes the Way We Think, are essentially catching the issue. The work which is in front of us, the research community, and you students as future members of the research community, is actually to put this at work. And so what? So I hope you see the the issue, no? Because the issue is that on the one hand we have a successful set of principles which are actually developing a technology. On the other hand, we are clearly going to hit a wall. No? If you think hit a wall, also not metaphorically, no? Because if you think to what happens to Asimov, and I don't know if you had time to look at the Dennett bomb robot, bomb disposal robot in Roth's book, but the problem with Asimov is that it is very well carefully engineered, but it's error prone when it put the foot in the wrong place on the stair. Of course, what you can do if you have the time, have a look to this Dennett's example. Of course, what they did, because this movie is from a few years ago. What you can do? Okay, you can add a set of routines managing the situation when you put your feet in the wrong place. No? So, and according to how far you are from the proper place on the step of the stair. No, if you are here, it's okay. If you are here, it starts to be a bit unbalancing. Here, it's risky. No, so you put a number of if and else in your big routines. You write a lot of software, and then it will never fall again when taking that stair. And then you will have a snail chair, right? And so maybe you say, so I also have snail chairs. And you will have to write another set of, several thousands of tens of thousands line of codes. Of course, this can work to a certain extent, but cannot work in any case. For instance, no? And then the problem is that, I don't know if you want you think probably we are overwhelming you, but maybe some of you want to try to give an answer why an emergent behavior or a self-organizing behavior could help to avoid to add 10,000 of lines of codes to the robot every time that they detect that in some specific condition it fails. Maybe you want to try to elaborate on this now. So why self-organizing behavior should be better than having a pre-designed behavior? Why? Because, or if you want, in what conditions? Because in some conditions, in a factory, maybe I don't need it. I know already everything. But please, so why self-organization should help with respect to pre-designed designed behavior? Any guess? Sorry for my voice, but I also have a bit cold. Big cold. Yeah, we have a guest from here.
Self-organization can help an agent, an artificial agent to adapt to several environmental scenarios.
So this might be. So what's actually in your view so the strength, what in the environment is actually creating the opportunity for self-organization? So what's crashing? What's the problem with? No, I think you already told more or less what we are looking. So it's uncertainty. So the problem is that the designer doesn't know at design time where the robot is going to act, what is going to act. Of course, it's really very well. I don't know if you have other opinions Because a variant is, and why we don't need self-organization in our factories where we have hundreds of thousands, or no, I would say at this point we have millions of robots in our factories, and they for sure they don't self-organize. Why we have so many of those systems and they work without any problem? Which is the other side of the same question. Any guess?
Coming from Plymouth?
Because robots in a factory hen are in a very controlled environment.
Exactly. So that's our trick. So our trick to avoid, to implement behaviors, nature-like behaviors, like plant-like also, or animal-like in our systems, is that we control the environment. So I don't need a robot. So while the Asimov, I think we may try to do a calculation of the, the concept of a medium time between two failures. No? How many stairs has Asimov to climb before falling, and you compare to the years that a robot can weld do its dirty jobs in its factory. That is around 8 years. So the medium time between two failures in a factory robot is about 8 years. Depends on, and it is growing. So, but the difference is that, so if the environment is under control, is kept uniform, kept aligned with the design of the robots and the environment, by maintenance. That's what maintenance is for. No? You go to the garage to make maintenance to your engine, because with time your car go away from the design characteristic that it was given at the beginning. And thanks to the maintenance, it go back to its supposed. And then cars actually don't have legs. No? You know this typical argument. No? But you need streets. So actually, no, you need streets. And what are streets? Streets are plain areas, controlled areas where the environment is good for your wheeled car. Because using wheels, so you don't have many animals. You have some example, for instance, of plants, no, the desert rose, which in certain conditions actually is a big wheel, no? It's big spherical wheel. So you have, and there are also bacteria which use wheels, but you don't have many wheels in the animal kingdom. Why? Because before the human manipulation of the environment, wheels were seldom useful, very, very rarely useful. So this is the point. So we have problem with the classical approach, and so far we have coped with them by maintenance, by building structured environment. The big challenge today for robotics is to use the perception systems, the good old-fashioned AI perception systems developed for the wild, for instance, in the industry setting where the environment can be controlled. So if you think about it, you need less intelligence if the situation is very repetitive. The more you surprises you can expect in the environment, the more you will need to self-organize behavior. So you will have to invent the way to cope with the problem on fly when you are in front of a problem. So, and what Asimov was not to do in that situation was to detect a situation that it wasn't designed for, which was putting the feet not exactly in the right place, and it wasn't able to invent a proper behavior on the on fly. And but you know that we also humans and even cats can fall, right? It's not perfect, so you don't have a perfect system which will always be able to cope with unexpected situation. But so to speak, the range of situation that an animal or a plant is usually able to manage is much wider than that of today's robot. Also, a question for which I don't have an answer is whether a self-driving car needs or not some kind of self-organized behavior. And if you think about, and again, people tend to think that theoretical issues some are on one side, and on the other side we are the business world where you don't care about theoretical issues. Actually, saying this question, do they need self-organization to have a really working self-driving car, or don't they? And if so, why? It's an economical issue, because if I start to invest, and many companies, a famous one is Tesla, are investing in self-driving, and at some point they realize that it cannot work. It would be a dramatic failure. No? So it's not true that basic research questions are unrelated to business questions. So actually, the big business questions, so those that can create an industry from nothing, an industry of billions, making billions of dollars or euros or whatever, or from many times are significant theoretical advancement. So I will give. But for instance, the cell phone it works because of some very smart people did very big progress in theoretical communication theory. So I mean, this is something that. Okay, so this is the. So we have two paradigms. Rolf told already this. One is cognition of computation. So it's this idea of gears and pulls and levers. Yeah, but it's much easier if you have a computer, because you can do many more things, but it's basically the same thing. And the other is, which is the challenge, and is what is now basic research, is cognition as an emergent process from sensory motor and interaction processes, which seems a kind of holy grail, and it's something that we are actually starting to do. So it's a situation. I like to compare. So it might be overreaching, but we might be in a situation similar to when Copernicus understood that the Earth was not the center of the universe, but was not circling around the sun. Copernicus had no proof of that. He only could say that it was easier to predict, that it required less calculation to predict the movement of 5 stars in 3,000 that are, because you don't know, but depending on your sight, in a good night, in a clear night, you can see from 1,500 to 3,000 stars. And there were just, and with naked eye, you can see just 5 planets. And in 3,000 stars, there were 5 stars with a behavior which was not explained by the assumption that the Earth was the center of the universe. For 5 stars in 3,000, Mr. Copernicus, a Polish astronomer, actually was a priest, not an astronomer, was an amateur scientist in modern times, he proposed to do something better. And those 5 stars were easily. So this gives you so I think we are in that situation. But we had no proof. We had to wait until Newton, a couple of centuries later, to have an explanation of why that was the right way to think. But it took 2 centuries to develop. Luckily now, you know that there are more researchers active now than the integral of all the history of humankind. So we might go much faster. But I think that if you read, for instance, Rolf's book, but there are also other people, not just Rolf, But this is a kind of blueprint. So a set of principles. We have the challenge of transforming that because when I say emergent cognition, but I cannot define very well. Emergent, this is better. So it's like temperature emerging from the motion of a molecule. From sensory motor interaction processes, I understand that it is a different thing. I understand that it is what happens in the cell. I have to develop a number of interesting models to be able to exploit it in the design of the system. And this is exactly what, for instance, many research institutes are trying to do. Right? And then, just to avoid to give you the prize from the frame of reference competition, you know there is a frame of reference of competition when in the main lecture, the basic thread, because you know that we have a guest lecture which are considered kind of complements to the main thread, which is more or less articulating, hopefully not exactly redoing all the times the same thing, but you can find the recorded lectures, is so there is this basic thread and the guest lectures. When in the basic thread we don't quote the frame of reference, the first student that spots that we didn't talk about frame of reference issues in the lecture is entitled to receive, I would say, a Swiss chocolate or a Cantucci box. Cantucci are kind of biscuits in Tuscany. As a prize. So this is the frame of reference competition. So because the example that Rolf did last time, the ant on the beach. If you look at the beach, Simon's example, Herbert Simon's, this example was introduced by Herbert Simon, which was a kind of one of the founder of AI and probably one of the people thinking more deeply on the concepts underlying the algorithms, the poor algorithmic implementation. So this idea is that if you look at an ant moving, in this case, concept example on the beach, but if you think to any ant moving on any terrain, you will see a very, very, very complex behavior. And you might think that inside, so if you think as we usually think when we design system, you may think that inside the ant there is a supercomputer, and actually to a certain extent ants have a lot of neurons, and it's not absolutely completely clear what they do with the neurons, but they do a lot of calculations. But probably not for what we would say they do calculations. And they have this barrier. So what's the point? That most of the trajectory of the ant on the terrain comes from what? Sorry, now, no? I don't know. Now I try again to involve the audience, right? So maybe since you have seen this last time, you had time to think about. So if I tell you, that the ant doesn't use a supercomputer to decide the trajectory on the beach, from where it comes? Why this trajectory on the beach of ants is so complicated? What's happening? Any guess?
If you want to say something, just open your microphone and state your answer or your suggestion.
I see that in Spain someone is doing a guess. I see someone gesticulating in Spain. Maybe he wants to share with us his thoughts. Yeah. Oh, okay. It's just as Rolf said, essentially, most of these behaviors are reactive. So the ant essentially change routes because it's a small stones, and so if there is a stone, it changes routes on the right or the left of the stone, and go ahead until it gets a hole in the sand, or it gets another. So why is the dimension of the body, so the frame of reference, how the body, the agent is with respect to the environment relevant? Because if the body would be much bigger, it didn't notice these small stones. So actually, if you do this point experiment and you increase the body of the ant by 1,000 times, the behavior will be completely different. I would add something, just to confuse you. I shouldn't do, but considering that the mountains, the earth crust has actually a fractal nature. You may probably have a way to build super ants, that to be so very big ants behaving like the small ants, but they should be in a range of dimensions. So you should probably you have the possibility to build a long series of ants in many bigger dimensions, but not those, because you know the story of a coast. Of the sea, which actually, if you at different scales, it looks the same. At those different scales, you may have different robots, but this means that you can't simply increase the dimension of the ant. And then the problem that is strong, because why symbol grounding is a problem? Because it's a problem because I want that the representation of the environment that I have in my artificial intelligence emerge from sensory-motor interaction, because in a top-down symbolic approach, a good old-fashioned, I simply write into the robot, this is a pen. Where is the problem? But pens comes in very, 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 in many, many different fashions. So I fall again in the paradox of Asimov falling down from the stairs. But maybe at some point my robot will find a pen that it cannot recognize as such. So one of the biggest problems in perception is that if you change the shadows, now you have seen when I switched on the light, suddenly a group of people emerged from this room, right? This for you, it's much easier than most artificial perception systems, because more or less you have a clue. So actually, we will see it, but actually we can devise a human from a very limited number of small lights. So this is I will show you in coming lecture. But if I put a number of small lights on my body, and then I walk in a dark room, surprisingly, most people is able to understand that there is a person. And people who knows me are probably even able to understand that, to recognize me. This is very, very difficult to implement in a top-down perception system, so in a good old-fashioned, and this is one of the things that we should want. From our perspective, we have our own problem, cognition as an emergent process, is that how we put the name on the things. So how I emerge, I write on a tree that it is a tree. how I write on a house, but it is an house. Huh? So, apart from the workaround that people use, for instance, in home assistance robots, I just say, this is the fridge. With some pointing system or just writing into the system, this is the fridge. As I told, the problem is that not all the fridges are the same. When we talk about the fridge, we don't have an infinite number of fridges. So I may even think of implementing in the system all the possible, but then I can see the same fridge in the morning, in a room, or in another room in the afternoon, or all these things again lead to the falling from the stairs issue. And again, really have a look to Dennett's example in Ralph's book, because this is exactly what you think. There is a solution. The solution is adding other code, and then adding other code, and then adding other code. And this might be, in many cases, what we don't actually know is whether this leads to a problem at some point or not. So I really think that is the number of line of codes that I have to write to manage in the good old-fashioned way all these unexpected situations limited. So it's something that while putting 1 million programmer at work I will fix, or is something that is going up exponentially, and at some point I don't have enough programmers, so I can't even think of doing that. This is to a significant extent an open issue. We actually don't know. So because what happens at many levels of frame of reference is that we have surprises, right? So you know, this is we are getting, it's coming late. It's started to be a bit late. No, so two typical examples. No? A macro example is that while finding a short path to Asia, Columbus discovered America. Actually, he wasn't even aware of having discovered a new continent, right? And then, in a moment, in the beginning of the 21st century, everybody was expecting a continuous growth of the financial markets, a continuous growth of prosperity everywhere, and suddenly nobody understood very well, and still people is arguing about what really happened. We had a dramatic financial crash, and still Europe and many other areas of the world are struggling to recover. This was a complete surprise. So you can have good surprise, discovered a new beautiful continent, or bad surprise. You can get into unexpected troubles when you think that everything is going okay. So I think I have to finish. Yeah. So the carry-on message is that we can do many things with mechanical automaton paradigm. That is what basically we implement most of the time still. But there are serious difficulties so it becomes very complicated. So we have to write much more software. Next time we will go deeper into this. Now, I just want, if you allow me just 2 minutes. Sorry for, so you see a kind of preview of what we are going to see. Because so we may finish with 2 movies now, because if Nathan wish, we may show 2. One is the Corner Ranger movie, and the other is the now walking down a ramp movie. And then we finish. So this is an issue which surfaced while I was discussing before with Olivier, no? Because if you see this in terms of autonomy, in terms of energy, this example is the corner ranger working for some 60 kilometers, something like that. So much more than any other robot. So if your objective is to reduce energy consumption, passive robots, so exploiting morphological computation, because there is no memory in this. So essentially the control here just give a small hit at the right moment to continue to keep a movement which is essentially a pendulum movement. So what the control does is to, at a periodic time, to give a small compensation of a friction, right? Because this is an inverted pendulum. You can check this by yourself if you want. So this is very nice. And now we can see the now walking down a ramp. So what you see? No, you know why I like this? I like this because the design of a corner ranger is actually based on a toy of the 19th century, which was able to passively go down a ramp with no control and no energy consumption. This is the same experiment performed by a now robot. You see, it's much more difficult to perform, right? Look how it works. If you compare the corner ranger movement to the way that now goes down the ramp, or if you again check for Ruina, Andy Ruina, and Collins and others, you look at the so-called passive biped walkers, they are much more natural. So if you look at this, seems very unnatural. No? It's like a scared person. So again, about intention attributions, now seems scared to go down the stair. Does this mean that now it's bad? Well, no, because there is a clear issue. No? Now is not at its best here, but it can easily outperform the corner ranger if the task is to wave hands, or if the task is to entertain children. So the big challenge from the scientific standpoint is how to implement in a system with a range of behaviors of a system like now, exploiting morphological computation, self-organization, and we will quote in another occasion, softness of material. So this is an open, and so I think that since we are out of time, we may finish here. Thank you. And sorry. Okay, goodbye everybody. Hope to be in better conditions next time.
Bye.
Bye bye.